Oh, the thing is on. It says we're alive. It's a Saturday evening. I guess what's going on? Memes here. Yeah, yes, I know. I use the term dimensionless gauge couplings. Yeah, kind of reiterating yourself there, because I think by their nature they're dimensionless. Again, I'm slowly learning. Here's the thing. I don't have a PhD in mathematics nor physics. Take that as you would. Feel free. You don't gotta be around here. I'm sure plenty of this stuff is wrong. Now, the question might be, is there something interesting here? Because, well, most ideas might be wrong. The benefit of humanity, it's you put some ideas out there. Someone else gives you some information. You get some more information. And all of a sudden it starts to congeal together. And perhaps, just maybe, we can figure out what's actually going on. I forget which finger was going up there. Something mirror imagery and everything. Welcome, Rick. It's good to see you. We'll talk. We'll talk. There's very interesting things. It's part of this is I've been going back and forth with Casey and everything, and occasionally we go back and forth, and then it's like every once in a while you talk to somebody, it's like I don't know what it is. I know Thad's told me this. Every once in a while, it's like I'll talk to Thad, and all of a sudden, it's like his eyes light up. It's like all of a sudden, I just thought of something. I have no idea why. I'm finding, and again, I don't know. Maybe just nothing. Maybe it's just me getting excited about some things. But sometimes when I talk to other folks, all of a sudden things just start to click, and it's like, is it clicking in the right way? Maybe it is. Maybe it isn't. But then all of a sudden, it's like I had not considered that before. So I feel like that's an important thing to be able to learn and just kind of figure out what the heck is happening. Because I don't know. Welcome up, Cycle. Good to see you. Yes. All right. So we're going to talk about some stuff. Okay. Yes. The over oppressive thumbnail that I use just because I'm just like, all right, I just need to put this here because I didn't know of anything else to do. So I literally just took a picture of the Wikipedia page as I'm slowly learning what different parameters like little g might. God. See, I think individuals like me sometimes now. Am I necessarily going to say ChatGPT solve universe? Maybe it can do that. Maybe that's a coming model or something like that. But it's when like I don't know what this is. Let me take a quick screenshot. It's pretty good at visual analysis because the same people made Dolly and stuff like that. And I'm watching Nerdy Rodent diffuse all these pictures into like full animations, and I'm like, oh my god, that's pretty damn good. But what I'm saying is sometimes it's like, what the heck is this squiggly little thing here? Oh, that's actually this. It's like, oh, I don't think I ever finished my Greek. To be fair, I don't. Did I even take Greek? I took Latin 1, and then we took Latin 2, and I think one of our teachers had a mental breakdown. We were terrible. I remember being a kid, and sometimes kids can get nasty, but it's not what we're here to talk about. Let's talk about some dimensionless gauge couplings. Oh, God, I wanted to talk about this for a while, and I'm just like, I'm gonna anger all my math friends and stuff because it's like I feel like mathematicians have a very special term for that, but then you start going through it, and again, maybe it's just maybe Wikipedia is all just ruined and all the other articles and stuff you go but allegedly people started using this when they were developing stuff for the weak sector to figure out it's like wait a second, these things appear to be non-abelian. Now I'm not going to pretend like I know all the difference that basically abelian means it's commutative, aka your order of operations. It's like it's just going to follow the standard. It's like all right, parentheses, exponents, multiplication, division, and stuff like that. And it's usually gonna work out well there. Non-abelian, again, to my knowledge, is um, yeah, the order matters. The order matters, and apparently, a whole bunch of folks that were working on the Nambu Goldstone bosons and stuff like that, and Peter Higgs et al. And a couple other groups, they're like, well, what if we just, what if we proposed it was like a field here and need the break and stuff like that? Yada, yada, yada. Spin unitary group 2, SU2. It's a horrible, probably atrociously inaccurate story, but to the whole point, while developing these things, the concept of, well, they use gauges for railroads to kind of feel like what's going on, and at that point I'm like, all right, I'm just gonna do this thing. People can feel free to correct me. Why do I say this? Okay. We have this big thing here through the yellow text. Dimensionless gauge coupling. It literally just says like coupling constants or something like that under it. And then I give this thing here where basically you got like 1/4. That seems to be a dimensionless factor. You got your gauge factor here, square, and then the TR is a trace, and then the big G's of the field tenses the other way. And again, I'm not going to say like I understand all this mathematics. But I can do this calculation. Wait a second. What's this? All right. So this is essentially the dimensionless version for elementary charge, aka the charge associated with a proton or an electron. Okay. Now they give this here, so you get your elementary charge. What are you dividing it by? You're dividing it by this crazy square root, which is the electric constant, epsilon naught, aka the permittivity of free space, times h bar, the elementary unit of action, Planck's reduced constant, times c, the speed of light. For those of all you that don't know, normally if you have this divided by not the square root of that with a 4 pi in there, basically, yes, you get alpha, the fine structure. Excuse me. You get its amplitude. You get Joe1. When this whole expression is squared, then, yes, you get the actual probability, aka your 1/137-ish, the fine structure constant, which you can reduce it to this. You square root this, so you get the dimensionless thing. Yeah, okay. Why do I say that? Because, well, when you do that, the elementary charge of square root of epsilon naught h bar c. Yeah, you get that 302, 822, 12, yada 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 number. Okay. Now, the question was, okay, because I'm a very simple dude, I'm like, can I just replace some things and see what may be able to tell us a story? Just using basically the same thing. Long story short, I just went hours going in things where I'm like, oh, well, this is I'm like, then eventually it's like, hold on, let me take out this. I'm just doing the stupid loop thing. I'm getting the same thing, and then I'm just trying to self-justify. Kind of like when Hans called me out. It's like, well, this is already the built-in assumption, and you're just looping around there. Now, it might be interesting. You might ask, why might this be the case? But if you got a loop in your logic, then it's kind of going around in circles. Now, under certain circumstances, maybe that's what we want, because things do tend to come full circle, I claim. So eventually I went back and forth, trying this, trying that. Got really frustrated. And then I'm like, wait a second. What if I actually like used logic and like tried to prepare? Or I'm like, what if I looked at this thing and be like, what would I need this to do for this to be true, no matter how crazy it is? So basically, we did the whole dang thing. So I'm like, all right, rather than elementary charge, I just take the mass of the Higgs boson. And again, it's just from Wolfram Alpha, so it's not necessarily using the most up-to-date thing. It's only a couple of significant digits. All right. So we got that. Then let's divide it by the same thing. What? Square root electric constant. H bar C. Note, one of these had to be changed. We kept the square root H bar and C. The thing that was required was 1 over big G. The inverse Newtonian gravitational constant is the one thing that must be entered here. Now, people could argue about that because particle physicists tend to believe you set h bar and c equal to 1 within particle physics. A lot of times, at least according to Professor Carroll, one of the other things that I heard from like, I don't know, a month or so ago, it's like we don't tend to set big G equal to 1. However, is this where we postulate it's like with a physicist level of rigor? Oh God, I don't know. Yeah, basically in order to get the thing to work, and again, this is probably just a naive thing, and it's kind of because what ends up happening? How did we get here? Basically, we're at least using that same ability to try to figure out what the dimensionless coupling might be to elementary charge by using this form. You take a thing, you divide it by the square root of all this jazz here. Now, why might this work? Because, well, spoilers. When you put all this stuff together, you just get the Planck mass squared. Oh, excuse me. When you put all this stuff together, you get Planck mass squared, and then you're taking the square root of that, which is just the Planck mass. So you're literally just then get the Higgs mass divided by the Planck mass equals this thingy. Because technically what this is, when you include the 4 pi factor, and here's the only real difference here between this and like the fine structure constant is if you throw 4 pi in there, you're going to get your Joe one. Actually, God, I'm just talking to the picture and going back and forth. Hold on, yes. I know. Oh, gee golly, an inverse big G. Who would have seen that coming? All right, we continue. So let's actually go over to the things. So let's share with a class. One over here, blah, blah, blah. All right. Let's go. Let's do another one. Now let's follow at least the base logic. So let's just do let's change this. Elementary charge. So at least Wolfram Alpha has that's like 10 digits. And then we're going to I have no idea what this will actually compute to. Okay, that doesn't really mean anything to me, but there seem to be some connections that hold over different stuff and things. So let's just put in our electric constant. Electric constant. Okay, so we get this number here. So let's bring up where were we? Standard model mathematical formulation, blah blah blah. Okay. Now, have I computed everything here? Oh, heck no. Perhaps if one's trying to figure out what's going on before we try to solve for everything, perhaps we should just try to solve one thing. Or at least get a better idea of what's going on. Yeah, there's a lot of math on all this. Don't worry, okay. Higgs stuff. There we go. Okay. Root 2 things. All right. The vacuum expectation value, we went through there. We've also conjectured a bunch of stuff. Let's go over here. All right, I've done some of that stuff. All right. What we're gonna look. Oh God, where did I go? I went past it. Blasphemy. Oh. I was supposed to be looking for another article. Oh, hold on. Let me, we're conjecturing, so let me cover my butt. Let's, give me like 23 seconds. Professor Wolfram et al., please entertain the people for the next, how long is it? What the heck is it? Oh, God. All right. For at least the next, 30 seconds.
Although this is going to be weird. and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might
Yeah,
be just
instead
hyper Rulial turtles all the way down.
yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
I'm almost there. I forgot which. God, when you have far too many. Oh, duh. Maybe the thing that says coupling constant, noob. Alright. Let's, Oh, yeah, who knew you're gonna title a stream something? Maybe it's the actual thing that says that. Alright. Okay, so they're going over relationships between different things. So, like, big G, for force, it's like, you get your mass 1, you get your mass 2, you divide by r squared. For Newtonian gravity, and for the Coulombic force. Is that even a word? Coulomb force. It is, you get your Coulomb constant of proportionality. You get your charge 1, you get your charge 2, you divide by your r squared, bada boom, bada bang. Okay. Oh. I should probably go back and actually reread all these things now, because I'm like, oh wait, I may or may not have read these before, and a lot of times like, now it's like, wait a second, I know what some of this stuff means now. I know. Okay. So as you can see, they go through here, they explain the fine structure constant, your standard, blah 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 blah. Okay. To be fair, that kind of was how we got here, because it's like, all right, I can do some things. Is there a more, let's say, rigorous way to try to see the connections with reality rather than just being like, oh, here's this alpha thing where we can just do like, just because this may or may not have the thingy where it's like, all right, I got my elementary charge. We square that thing divided by our 4 pi electric constant h bar c. Okay. Hey, I realize I literally just typed that all out again, but the reason for it is just because, okay, you get that thingy there, and it's like, ooh, it's a dimensionless number. Then you're like, wait a second. This is elementary charge squared. If you get charge squared, all this jazz, and it gives you a dimensionless number, that must mean this is charge squared. So when you do the square root of that thingy, it's, oh, looky, it's the Planck electric charge. So that means that this whole thing, you can simply rewrite as Planck charge squared. And for the sake of notation, less keystrokes at bare minimum, you can just write as elementary charge over Planck charge, entire expression squared. Okay. Because this is kind of how we got here, because it's like the ratio of the Higgs mass to the Planck mass. Some may say it's a issue of naturalness. That, why there seem to be 17 orders of magnitude between this thing and that thing. Look, 17 orders of magnitude. That don't make sense. Fortunately, Wolfram Alpha at least has at least enough accuracy and digits in here that when you square that term, it's like, if this 1.05, if that 5 never showed up, I have no idea. Just being very neurotic and having a semi-videographic memory at a whole bunch of things, if I look at them enough, and pretty good at remembering exponential powers, it's like, oh, wait a second. This, looks to be about the magnitude of, Planck's reduced constant, h bar. And again, depending on the numbers you put in there, seems to hold. We've got that at 10. And again, It's probably the first calculation where it's like about 1 joule second. And again, that's about. So then that raises the question. It's like, wait a second. H bar we've got defined at 10 significant digits. The Planck mass, we have 7, but the last 2 have error, but we're really confident on like 5 significant digits. The Planck mass, we have confidence like 3, about somewhere in there, and then we've got our error bars for the next 2 digits. So it leads to the whole hypothetical. It's, well, what if we assumed it was true? We just set it equal to h bar divided by joule seconds, and again, this is just the crazy part there. Why actually like some fundamental unit or something like that actually have meaning? I mean that's just our reference. We defined this. Could we be so lucky? So I'm not, and then like it returns true. It's like, why is this? And again, it is estimating. I actually submitted a ticket because I'm like, we do not have enough information to say this is actually true. Actually, to be fair, I didn't even mean to do that. I was going to say, like, well, hypothetically, if this statement were true, could we leverage, I don't know, the 10 known digits of this? This is literally just a 1 in the system. This has got 5 digits. We know this to like 3. Let's solve for xkg. And hence why this other thingy that we had back here, which was, long story short is, again, all this jazz ends up literally being, before you take the square root of it, it's literally just mass squared, because, well, because that's what it is. But I digress. We go back, okay. So we got mass squared over there, blah, blah, blah. It gives us this number here. And there's an interesting thing. I often ignore this because, just because I don't want to have to deal with it. So I usually just do that square root over, square root of h bar divided by joule seconds. The root of that whole expression. Okay, and then you multiply it by the Planck mass. And basically you get this. What that expression does not return, or at least Wolfram alpha, is we're solving for a square there. That means our x could technically be positive or negative. Now, if this were the case, and you had some, oh God, I feel like there's a negative mass conjecture or something, but then again, people, when they're doing their accounting through virtual Python, oh, okay, well, maybe we can have some violations. I don't know if that makes sense. I don't know enough about group theory and everything. Uh-oh. Hold on, let me make sure my mic is still working, because my other earbud just conked out. All right, we got that. Blah, blah, blah. Let's see, is it going to stay if I actually charge this? Blah, 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 blah. Okay. It still says it's going. I don't mind me. I like my anime music running in the background. I'm so terrible. I didn't even charge half my ears. Can't take me anywhere. There we go. All right, where were we? Blah, blah, blah. That's the mathematical model. Okay, we wanted that. Okay, so long story short is, well, let's just do this. So that thingy over there, we get, you do this whole jazz. You do your elementary charge over the square root of all that without the 4 pi. Because the 4 pi from our our fine structure constant. What happens if we were to put 4 pi in there? Just, I'm curious because they kind of removed it. And then basically did the square root of elementary charge squared and the denominator. So it's like, all right, well, let's just throw in, what am I doing? Oh yeah, 4 pi. 4 pi. Yeah. All right. Okie dokie. Oh, for those of you not familiar, this is Joe 1. This is the amplitude of the fine structure constant because I think I already had all my brackets. Did I have all my brackets? I did have all my brackets because when we square that, we get our number over here. Not 0.007729 73525. Then we argue about the 10th significant digit because apparently we only have 9 significant digits for the speed of light, but then again, results of experimentation may vary. Perhaps it depends on how you perform the experiment. That's, I don't know, maybe it's telling us something. Maybe Thad's calculation's off and he needs to divide the Planck mass by √2. And then it eerily seems to fall right within the new error bars, which are really dang small, but I digress. All right. So long story short is let's go back. So what happens? If we take the 4 pi, if we take our spherical structure out, let's say, we get that dimensionless thing for there. Now, why are they using that? Long story short is, if you throw your... Oh, I need to divide it by 4 pi, isn't it? Divide by 4 pi. Oh, because it was in the denominator, derp. Well, actually, it should be the square root. Okay, never mind. I'm talking hot garbage. But, okay. So what happens if we do this? Okay, here's what I actually meant to do. Let's change this. Let's change it to the Planck charge. Why am I showing you this? Because it gives you another dimensionless number, but I'm like, oh, wait a second. If this is the maximum of charge, I claim, shouldn't we have a notion of oneness? That's where you need your 4 pi. Because then we get oneness. Oh, wait a second. We've got that. If we have the 4 pi, we got oneness, the Planck charge over that, and elementary charge. Swap that with a 4 pi, it's like, oh! It seems to be the amplitude, the electromagnetic coupling constant. You square it, you get your probability, you get your alpha. I'm like, okay. That's kind of cool. So let's go to our... oh, I'm sorry, I jumped ahead. Okay, long story short is if you set this up and you take math seriously and you think this is the base expression, you have a positive and a negative term. We're just going to play with a positive for right now. So we're assuming kilograms. Yeah, and again, it's only showing us this. Let's do it c squared because it's easier to remember, just at least for me. Okay, sure. 125.37. I'm gonna add the 6 onto that because that's at least when you actually incorporate the rest of the digits. I got the links to it still below for the derivations and everything there. And interesting things happen with this number. And again, there's an uncertainty of technically plus or minus 2 at the bottom here. So go up to 0.378 or down to 0.374. That's also seems to be the threshold up for some other interesting things. So, again, just trying to latch on and see if we can't figure out interesting things that might be going on. Welcome, Mark. Good to see you, my friend. Good to see you. Oh, got different folks rolling in, rolling around, saying hi. Excellent. All right. So, why am I showing this again? Oh, yes. Basically, we just wanted a better number for that other thing. Rip that there. I'm like, okay. So what happens if put this in here? So, oh, we need mass, so we just need to divide by c squared again. I realize I probably didn't need to do any of that, but that's I realized I was repetitive. Okay, so let's just throw this in here. So give us out a mass term that we had there. Okay. Now, again, we have this number here. Well, what happens? What happens if you were to square the whole expression? That number looks kind of familiar. It's kind of like the elementary unit of action. Oh, there's a joule second. This time, and again, should it really say it's this? No, you shouldn't say that. Because we don't have all the digits, but at least to the level of confidence that Wolfram Alpha is giving right now, that it's also because, well, this number was literally tuned by that, because we literally just went through the whole rigmarole of, yeah, having the joule second in there and then dividing by. Should we be surprised? Oh, this is another way for people to go if you don't want to trust any of that, or you're like, oh, this is weird. You're saying that the joule second is something about that. It's like, okay. So, I mean, we could do that, or I've got this. Let's just square this, do the same thing. Give us. Okay. It's going from stating it's that to saying it's approximately that. And that's kind of how we got here, because it's like, that's interesting. What if I assumed it was true? And that, my friends, is how we went down quite a Wolfram hole, and wiki holes, and archive excursions, and different IPOPs, and also approximately 10 to the 7 ergs. So if we... I'm sorry. Oh. The erg. Erg seconds. A very underappreciated, I believe it's now depreciated unit. Or is the erg second still used? No, ergs are usually depreciated, but these 10 to the 7s are quite interesting. Perhaps if these units weren't depreciated, perhaps they would be more appreciated. Pun intended. So, moving right along. And again, it just happens to come to about the reference that we set for that, even just putting in just... Listen, these are just all things that are listed on Wolfram Alpha. And again, are there higher precision measurements and stuff? But it is a curious thing. So we've got... Basically, we do the exact same thing that they did over there. And then we get that. Actually, I could probably just rewrite this whole dang thing. Just... Higgs mass over that. I think actually maybe this was one of the first ways, but then I think it either got ugly or the way Wolfram Alpha stacked it I wasn't a fan of. Okay. I mean, that's kind of a short thing, but sometimes if you throw the parentheses around it, it makes things neater. Or maybe it was because how many parentheses do I need? Okay, maybe it was because it was like this. It was a little bit of a stack. It's like, get a Higgs boson mass, divide by the Planck. Oh, let's enlarge this. We can do that. Boom. Magic. Enhance. Oh god, that's far better. There's an option to just do it. Alright. So, long story short, for our whole electromagnetic thing, it's like, I got that. Let's do structure constant. So again, it gives us this whole jazz here. Okay. We got this whole thing. And that's like, oh, wait a second. We can have a shortcut. Some may say if we could computationally reduce it, or at least for me, rather than writing out all this jazz every time, it's like, wait a second. Elementary charge over Planck charge. Square the whole dang thing. Let me throw in some brackets just so we're nice and pretty. And I just like looking at things next to each other. Okay. So we've got this. We've got... I'm getting other ideas here. I'm sorry. I get so distracted by things, all of a sudden ideas just start popping up. I'm terrible. Okay. So let's just go here. All right. So we've got our elementary charge divided by our Planck charge squared. It gives us our alpha. Okay. If we want the amplitude, divine structure constant, we just take out the square term. And we get that. Okay. Just noting that. So, if we believe there may be patterns in nature we can pick up on, because certain things we might recognize. Okay. So, hypothetically, if we take the same intuition, if we're like, all right, this is the coupling constant of electromagnetism. Or this is the coupling constant for charge. Is the square thing. And unsquared, it's this ratio between elementary charge. So we got an elementary unit divided by a Planck unit. We got another elementary unit divided by a Planck unit. If we were to square it, this would be the coupling constant. It's the coupling constant of mass. What does it seem to be proportional to? About the magnitude of h bar. I mean, should that actually be surprising? It's, and again, this is conjecture. This is conjecture. I don't know of any well thought out actual, because again, you're gonna need to have some group theory, and I know Rick's talked about spans and stuff. You're gonna actually need to connect this into the standard model and saying, well, this is a thing nobody's ever heard of. It's got a couple of significant digit relationship. I have nothing else that can justify this. Believe me. I wouldn't believe me. I'm still not sure if I believe me, but it's an interesting pattern, and I'm just like, okay, well, what happens? What happens if we, like, literally just, I don't know, Planck mass? To be fair, I actually don't know what happens here. Okay, it gives us that 10 to the... Oh, we're literally just canceling it out. Derp. Because it's a really small number. Okay. So I'm like, is there something we might be able to learn? So, okay, let's do this. So I'm literally thinking this here right now, because if we do this, we get this constant proportion. Oh, okay, wait. Oh, I'm dumb. Like, charge. This is the dumbest thing in the world. Okay. So, is it a bad thing that all of a sudden it's like you may say things, it may be right in front of you, but then you don't realize it until the exact moment where I'm attempting to explain it, questioning myself like at every moment, saying, wow, this is going to be wrong. And eventually you're like, oh, wait, this is actually kind of makes sense. Okay, so long story short is elementary charge over the Planck electric charge, bada boom, bada bing, you get the amplitude of the fine structure constant. Okay, or Joe 1. When you multiply that ratio by the Planck electric charge, you get one elementary charge. Why? It's just you're canceling it out. I mean, look, you're literally just doing the thing. Okay. So, what happens if we literally do the same thing? This is okay. I'm realizing at the same time this is just, of course, it's going to do that, but okay. Just for my own naive algebraic skill. I mean, again, one, that's the obvious thing, but I'm coming at it from different ways because Thad shows me that ratio, and then he does it, and then even if his charge seems to deviate from whatever is unwool from alpha, it's like it ends up still uniting at elementary charge. Is that why his prediction deviates around about the 10th significant digit for the fine structure constant, but it ends up uniting at the same parameter? Maybe that's just wrong. Maybe he needs to divide by root 2. I don't know. Maybe there's something going on around the 7th decimal place upon some empirical law that may or may not exist. Again, this is just the obvious thing. I'm just an idiot for just seeing this. But okay. I'm sorry. Sometimes it's like I have something in my head and it's like I just need to see it and just see, okay, this gives you this gives you this, because this is the ratio between this and it should be a duh thing. And then sometimes you just square the thing, you get an amplitude for different things, and excuse me, the coupling constant. So I don't know. Again, group representation are required, but I'm like, okay, if this is the I'm avoiding the whole dang thing that I came here for, to try to look at this crazy thing. All right, let's go back. I apologize. I've been neglecting. Structural in Cycles commenting, this feels akin to metamathematics, not metaphysics in the causal sense, but a structural inquiry into the foundations of physical law. A physics of physics. That's deep, and that's a fantastic compliment. I mean, I don't deserve it. I literally gamer first and foremost. Like, okay. As somebody for a period of my life that spent about 18 hours a day playing World of Warcraft, working at an overnight security job where you can play about 6 hours of the day and just walk around the building couple of times and stuff. It's make sure things aren't burning down. All right, no horrible things. Get your cameras there. It's like, I played a lot of World of Warcraft. And a lot of times if you're coming across like new boss or something like that, and they totally wreck your face because, well, one, maybe it's a bit of a higher gear tier, and then sometimes there's certain aspects of that that you don't know. And then upon reviewing after getting destroyed, it's like, okay, so before everyone died, approximately 12 seconds prior to that, there was a curse that was put on everyone. It's like, oh, maybe we need our mages to decurse everyone. Or maybe there's different parameters that are happening at different intervals. Stuff and things might happen, so you try to account for all those the best you can and optimize your strategy. As far as I understand, it's just, you might not say it's gaming, but it's like, well, what's the standard model? We're trying to help use mathematical representations that you might argue about the rigor in physics, but like, the math is math, and if you can put things onto a computer, the code runs or it doesn't. That's the thing. It's like, it works or it doesn't. That's kind of like the beautiful part about computation. I mean, I could sit up here and just like hand wave and be like, all right, so there's some parameter within our uncertainty of this or that or anything. That's kind of how I see it there. All right. So the whole part. Huh? Okay. We can go back to our, where were we? Oh God, I ruined all my tabs. Don't mind me. Okay. So why am I showing this? Because one, the interesting thing here is for at least charge. Let's enlarge our charge and stuff. Okay. So at least when you're doing charge for this particular framework, an elementary thing over the square root of h bar c and an additional constant. Okay. In this case, you take the 4 pi out and you get this number here that they have there, which is the square root of 4 pi alpha. So it has the relationship there. So again, we should not be really surprised at all. Did it just re-shrink it down? Let's do it each time? Okay, no. Move this over here. All right. So we get that when we throw in our 4 pi. So when we throw a sphere into the denominator and we divide it by a sphere, okay, get the amplitude of the fine structure constant, and then when we square it, we get the fine structure constant. Okay. Now, when we put the Planck charge in there, with dividing by the sphere, we get 1. Okay, so we get unity. We get a factor of 1 because all this ends up being the Planck charge. Yeah, spoilers. Okay. So what happens if we thought there was something to that? And let's use our, I don't know, let's just actually just do the Higgs thing. Okay. So go back. Apologies. All right. Wow. Okay, never mind. Let me just do this guy. Move this tab over. There we go. Okay, let's go back. All right. So we get this number over here. Now, what happens if we swap it from an elementary thing dividing into something? Well, let's do the Planck mass. The interesting thing is when we don't include the 4 pi, we get 1. When we include the 4 pi, it does change. What does it change by? The square root of 4 pi. 2 square root of pi. Because Well, that's what it should be. I think so. It should be 2 square root pi. Might need a... There we go. Oh my god, yay! I did the obvious thing. It's like, oh, well, that's there. It's also interesting because, wait a second. Don't mind me. I'm pretty sure that's the Planck charge factor. 2 times the square root of pi. Planck charge is 2 root pi. Reduced Planck mass is 2 square root 2 pi, I think. Okay, divide by 2 square root 2 pi. Okay. I mean, again, I may or may not be a wee bit spectrumy in some of these things. It's like, oh, hey, these are friends. And you ask now possibly tens of thousands of questions to Wolfram Alpha with hundreds. Oh, God, far too many. Okay, there's a bunch of single tabs, and then my high ones are 6 tabs, 20 tabs, 13 tabs. It's actually not too bad. Yes. Oh, cool. It. Like I said, I just don't know any better. I'm a monkey with a magic typewriter that may have an idea of where to look. Not because I'm any of these. God, just because it's the worst drawn Einstein ever. I know Einstein. It's just I have modern computational tools, and I've actually had some incredibly brilliant folks that have actually like given me the time of day and occasionally explain things to me. And the modern, okay, again, I came from more of a political background after getting tired of yelling at the TV screen. Get on, it's like, well, of course, with well-placed logic and good meaning, we can solve the world's problems. I wasn't able to solve the world's problems, folks. That's the thing. It's like, I want everybody to just get along, and I would love for it to be just sunshine, rainbows, us all sitting around a campfire, just roasting some s'mores, and unicorns can go around farting out rainbows and stuff. I think that would be awesome. I also have to kind of be realistic, and I couldn't find a way to unite people without a common enemy, and hence why my general MO is perhaps we should legalize dueling. The ultimate limit of what somebody believes is what they're willing to sacrifice for. And again, the Means of Destruction channel does not condone violence. Unless we legalize dueling and let consenting adults engage in mortal combat under the doctrine of bodily autonomy. Your body, your choice, maximum freedom, maximum responsibility. All right. After everybody was oh God, assume spherical Einstein. The terrible thing is, I'm going to take that spherical cow madness seriously. I think we need to do that. We need the spherical Einstein. Oh wait, no, Einstein is too spherical. Isn't that with like the covariance or something? Because it's 8 pi divided by the Planck force. Huh. I don't know. Where are we? Okay, let's just finish up the madness. What the heck was I doing? Oh, sorry. Okay. So basically the whole thing that I was trying to get into was when you put a Planck thing, basically for charge to work, you need your sphere. You need to get your root in there for it to be the sphere. For the Planck mass, you put your sphere in there, you get some deviation. You don't get your sphere in there, you get your 1. So it's interesting, the difference, at least, and again, it's probably nothing, but if a Planck unit, a boundary of reality, let's say, a boundary of charge divided by all this jazz as a sphere, or excuse me, as the root of a sphere, and the root of all this jazz, you get 1. Okay. With a sphere, you get a ratio, but without the sphere, you get this. Okay. So we've got the Planck mass. Let's swap it to the Higgs. Okay, and when we square that, we're going to get approximately h bar, but there is a little bit of deviation there because in the third significant digit there, it's about off by about 1.19, something like that. Which is about the magnitude difference there. Okay. I try to see if there's something interesting if we did 4 pi in here. So we're kind of just we're dividing a sphere by basically big G and multiplying all that stuff. Because the interesting thing is H bar and C is bending stiffness, which coincidentally is it's the Newtonian gravitational coupling with mass in the numerator. Rick had pointed out that allegedly the term didn't need to be in the numerator. It seems like a really weird thing. How could we have that freedom? Okay, so long story is I played around with some of these things. I couldn't without just basically you have to do the same thing. You have to do your I think we divide it by, is it multiply? No, it's multiply. So it's 2 square root pi should be the difference. Yeah. Okay. And again, it's rounding because it's like, all right, we only gave you a couple of digits there. Now you're incorporating this, and okay. That is more information than just the Higgs mass divided by the Planck mass. It just said 1. That 1 there, I'm like, oh, that's the problem right there. And it's like, well, Professor Carroll said sometimes, like, if you see something, you don't know what it is, square it. That's what physicists do. So I'm like, I did my little squaring thing. And then, well, what happens if you square it? We go back to that 1.05, and it's like, again, this is a dimensionless thing that shouldn't mean a dang thing, but if we assume that maybe there was some there, and then we can do the calculation, well, we seem to much closer fit that 1 joule second parameter. And oh my god, this can't be true, because that would mean that the joule second is meaningful. Wouldn't that just be it all? Which apparently equivalently would also mean that 10 to the 7 erg seconds are meaningful. Why on earth could this possibly be the case? I mean, that would mean like our units are unreasonably effective, let's say. Maybe it's just because how we parameterize this in a particular group structure of U1 cross SU2 cross SU3, and everything just makes sense, and we did such a dang good job, or It's not like the original kilogram was based upon water. It's because, well, I don't know. It's not like, what, like 1,000 kilograms is approximately 1 cubic meter of water, according to the conventional density of water. Now, to be fair, this is assuming water has that relationship. In reality, usually not being within water holds for about 3 significant digits or so. Now, if you are a little bit under the surface, sea level, and or maybe throw in just a pinch of salt, long story short, there exists a temperature and pressure where water is precisely 1,000 kilograms per cubic meter. Don't that just beat all? Thanks, Rick. All right, so we've gone over the hour. Okay, so just a review is, long story short is, we come full circle. It's like, I'm just doing naive things. I'm going around. I'm like, all right, well, what would you need to do this? What would you need to do this? I'm like, well, if I can just computationally reduce like the fine structure constant to, I don't know, just an elementary thing divided by a Planck thing. Okay. Yeah, its amplitude. What happens if I did, I don't know, an elementary thing divided by a Planck thing? You square that. Seems to be about the magnitude of this guy right here. That seems to be an important thing. And again, I'm just like, you kind of look at this relationship. Maybe you say something. Maybe show a few bits. Okay, yeah, maybe a couple of significant digits. It's like, okay, well, what would actually be behind this? And it's like, it seems to be a similar thing, and occasionally to get your oneness, the difference appears to be. Long story short is that's not a really satisfying thing. If you want to make it more satisfying, maybe you need to mathematize it. Maybe you actually need to look for what could a potential gauge coupling be, because apparently you'll have your like big V, and you need to have at least like 3 components are there, like 3 different fields or whatnot of different stuff interacting. Or again, I'm not a mathematician, and I'm very ill prepared for this. I kind of wanted to share some of this because I thought it was interesting, and I may or may not have stayed up far too late. Eventually being, oh wait, this, if I'm gonna take this thing seriously, let me literally do the exact same thing. And I went through the exact same thing, and then it's like you have to multiply by like voltage squared or Planck voltage or something. Now you're just adding in your epicycles, if you would. I'm like, all right, how can I keep this same dang structure at our H bar and C? I'm like, what would I need it to line up as? Well, the thing that apparently seems to line up with it is oh, sorry. This is the inverse big G. Now, again, depending on who you ask, but oh yeah, the whole other reason why I was kind of showing this is, again, we kind of went over this at the beginning, but in quantum field theory, the dimension of the coupling plays an important role in the renormalizability property of the theory, and therefore on applicability of perturbation theory. If the coupling is dimensionless in the natural unit system, i.e., C equals 1, H bar equals 1, like in QED, QCD, and the weak interaction, the theory is renormalizable, and all the terms of the expression series are finite after renormalization. If the coupling is dimensionful, as in gravity, where they express it as inverse energy squared, or the thermometer theory where it's also expressed in inverse energy squared. It may not work, but I'm like, all right, if it's dimensionless, okay, dimensionless. Now you can argue whether this is right or wrong or not, but okay. So rather than just saying it's the Higgs mass divided by the Planck mass is equivalent to the magnitude root of h bar, it's like, I mean, that's kind of, it's like, now I'm inserting the joule second, now you gotta explain that. Well, this is just the same thing that we're using with this. We're just replacing charge with mass. And instead of the electric constant, which perhaps it might be worth looking at this real quick. Because the electric constant is, oh, look, it's already an inverse. It's the magnetic constant times c squared. Oh. I probably should have clicked on this to remind myself of that about 2 hours ago. Oops. Yeah, but long story short is, we got our h bar, we got our c. Action, maximum speed, gives us bending stiffness. We do 1 over big G. Take the root of all that. We get this stuff. Okay. What does this stuff have to do with anything? Because when you multiply by the Planck mass, we now come full circle. And we get out the Higgs mass. Because that's what it's giving us. Because that is the Planck mass. We're literally just getting out the same thing that we did for one of these guys. Yeah, basically when I was just like literally just breaking it out, I'm like, all right, I get that. We get that thingy back. Just do that electromagnetism thing. Okay, never mind. I'm just clicking around aimlessly now. I was trying to find something else, but never mind. Okay. What? Why? Because, well, this is just. Wait, what did I do? Oh, because this is mass squared. We take the square root, so it ends up being the Planck mass. So that, okay, Planck mass, and then we got the Higgs mass. Okay, so it is the same as before. I'm sorry. It's just, in my head, I'm like, which loop am I caught on? Caught on now. So it's, at least, I'm attempting, and maybe it's telling us some other things, because I know Casey has been speculating that he thinks that perhaps there may be some potential group connection between some of these dark things that we seem to observe, and it's speculative, but there may be some connection between things that you don't publicly hear explored so much. Let's leave it at that. So, oh, no worries, Rick. I'm just wrapping up right now, so it's 10:37, so it's that's close to. We got a 137 in there, so. All right, so we're just gonna wrap up right now, and yeah, that's all I got for about now. And then yeah, basically in about the next week, I should be back in Utah, and we should be having a conference. For those of you that are interested in perhaps viewing, I know some folks might not be able to make it out, so I'm gonna coordinate on my end for perhaps a little bit of a web uplink and stuff like that. And again, if you're really interested and would like to contribute, that's something that we could make available. Just privately message me, and we can work on that. So other than that, that's all I really got. So Peace out, everybody. Take care of yourselves. It's a crazy world out there, but it's hoping for a better tomorrow, one day at a time. Peace out, everybody.